So we are Team Accelerate, and our project is the Specialty Parking Occupancy Detector. My name is Philip Davey, and I'm an EE major, and I was involved in the housing and part of the PCB design of the project.
My name is Yusuf Saad, I'm a computer engineering major, and I focused on the development of the websites hosted on the Raspberry Pi.
I'm Charles McNeil, I'm an electrical engineering major, and I worked on the telecommunication aspect of our project.
I'm Augustine Reyes. I'm also a double E major, and I focus mainly on the power circuitry and helping with the PCB design.
So around UTD, there are a limited number of disabled and electric car parking spaces. These are dotted around campus, so we wanted an effective, low-cost method to inform the user about the availability of these car parking spaces. Yusuf will talk about the solution to the problem.
So for our design, we developed a system that could handle a network of sensor pucks that all communicate with one base station that can encompass most of campus. Each individual sensor is in the parking spot itself, so when the car rolls over it, it can detect whether it's occupied or open, and then send that data to the base station. Each puck is both solar and battery powered, so that we can get a long-lasting battery life. It detects each vehicle through the use of an infrared distance sensor to get accurate measurements up to about 50 centimeters. That measurement is then sent to the base station itself, which is the Raspberry Pi connected to a LoRa, long-range communication receiver, which then updates the website in real time so the user can see exactly which spots are open and closed.
And through our testing, we found that the maximum range we can get between the base station and one of the pucks is about a half-mile. And as you can see through the light blue circle on our map, 1 half-mile radius circle centered on ECS South can actually cover the majority of campus, and our network could integrate a second base station if we really needed to cover all of campus.
Continuing with testing, we decided that, of course, our detection range for each sensor puck and the operability life that it would have were fairly important. For detection, we decided on a range of 50 centimeters because even lifted cars generally fall within that range. So the sensor we ordered during testing, we found that even though it was rated for about 50 centimeters, it detected accurately mostly between 48 and 50. So we did manage to meet that goal. As for power, we were aiming for a 5-year life of operability because that is what we had seen with competing devices. The device that we developed, given the fact that it is solar powered and the battery that we include with it is rechargeable, it looks to last about 15 years barring acts of God or just really bad parkers. And that's all really. We'll now open the floor up for questions.
How big is that?
So none of us are mechanical, and we have very rudimentary experience with SolidWorks. So the puck is about this big. You can kind of see the case.
It's about 15 centimeters by 10 by 5 centimeters.
But there's a lot of spare space in there, and I think someone with more experience could make a smaller, more robust apparatus.
So you tested multiple devices, is that correct?
Yeah.
Yes.
How were they addressed? How did you know which device was transmitting?
It would send a specific message from each puck, so that you could parse the packet from the base station itself, and there'd be a specific ID for each spot. So say this is spot 1, 2, 3, and it could tell from that. And then also expanding on that, you could also tell whenever data is corrupted if you don't get the whole message.
Each puck has to be programmed individually so that it knows which one it is and where that puck is going to be stationed.
So why did you choose the optical sensor since this is going to be installed outdoors and get dirty and
we went with the optical sensor kind of because it was the first thing we thought of. But the one we ended up choosing was very low power, and we thought that it would fit our needs.
And if we had more time, we would incorporate more sensors so that we can get a better reading if there is a car in the parking space. It's in like a wider range of sensors.
Did you guys test this under any kind of temperature load? Because, if you're sitting on a parking lot, Dallas in the summer, maybe you get up to 130, 140 degrees Fahrenheit. Did you test any kind of high temperature?
We did not do any sort of stress testing or temperature testing because the enclosure that we ordered, we had some problems getting it in so we weren't able to go out and do much temperature testing.
Then how did you forecast the 15 years?
That, of course, is based solely off of how long the battery can last, how much power drain we have for the device, all of that. The battery itself is rated to operate fairly efficiently up to, I believe it was 110 degrees Fahrenheit.
Okay.
That's part of the reason why it was chosen. The actual parts for the device are rated pretty similarly. So the 15-year estimate is actually a reduced estimate. The total estimate is about 19, maybe 20 years, depending on how continuously we run the device. So I just shaved off like a quarter of the time to account for any temperature degradation or things like that.
Was it Laura or Laura Wan?
It's Laura, not Laura Wen.
All right, let's thank the team.